Hi everybody and welcome to the second video in the Monster Text-to-Speech and Voice Cloning course. In today's video, we're going to try to understand how humans produce speech. And you may be wondering, why is that important? Well, before we can make machines talk, we really need to understand what speech, what talking is, because that's going to give us insight into how we can reproduce it synthetically in a machine. So let's get started. But what does make speech special? Well, speech is highly complex because it's information dense. There's a lot of information that we can encode in sound, which is astonishing, right? So it's not something that you should take for granted. It's really an interesting thing. And at the same time, speech is multidimensional, meaning that it has a lot of levels to it. It has the level of meaning, the level of language, sound, emotion, and identity. We sometimes identify with our speech, with our voice. Good. Let's take a look at the human speech pipeline, the way we produce speech. It all starts in our brain with our thoughts. Here we have like what we want to communicate to other people. Then those thoughts get sort of implemented into language, into words. Those words then get into phonemes that we start to articulate, and we'll see what those phonemes are in a few minutes. Then we start the articulation phase, so we just utter those phonemes, those words, and the result is just a sound wave that propagates through air. Now let's do the mirror thing with a machine, with a text-to-speech machine that can generate speech. Okay, so the thinking part of it and the language part of it is, we can think of it as a large language model, or a language model that generates like some thoughts, like some ideas, that gets transcribed into text. That's the language part of it. Then that text has to be transformed into some acoustic features, like for example a spectrogram, right? And then once we have those acoustic features, we can use what we call a vocoder. That's basically a machine that takes acoustic features and spits out an actual waveform that we can then listen to. It does like that translation. So these are the two speech pipelines, one for human and the other one like for machines. Of course, like there are different pipelines for machines depending on the system, the model, and so on and so forth. But these will give you a kind of like high level understanding of the different parts and how they sort of like map each other out. But now let's jump into more or less like each of these different steps for the speech human pipeline and dive into it. So thoughts from the brain to words into language. We move from brain activity into words and language. So we know that speech is planned before it's spoken, obviously. So you have like that internal voice inside you, like that generates like those words, but then you have to utter them, right? You have to produce the sound. But before you do that, you come up like with language, with actual words. And these sequences of words do encode a couple of things. They do have the semantic layer, and that is the actual meaning. So what we want to say, the semantics of a word, it's basically, it simply is its meaning. But then we also have in language the syntactic layer. That's the series of rules of grammar that we use to construct sentences that work well and can be understood by a collection of other people who speak, other speakers who share the same language. Okay, so in the language we have two levels, the semantic layer and the syntactic layer. And that basically corresponds to what text does in text-to-speech. So we start from this semantic layer and syntactic layer, and that's basically a given at this point, unless like we are doing like some like LLMs like before, like some reasoning and then come up with the text. In text-to-speech and voice cloning, most of the time we assume that we already have this level, the level of language, the text is there, we just need to to actually articulate in sound that text. Good. So now we have these words, we have this language. So how do we pass from words to sounds? Well, here's where phonemes come in, okay? But what are these phonemes? Well, we can think of them as the atom of speech. These are like the individual sounds that make up speech. And these are your vowels and your consonants. Like, for example, a phoneme would be a phoneme, a consonant phoneme would be t, for example, okay? But let's use a couple of analogies to understand what these phonemes are a little bit better. Let's drive an analogy with music. So in music, you have pieces of music. Pieces of music are like a melody like this one, Twinkle, Twinkle, Little Star. Is made up of a number of musical phrases, okay? So we can think of a word in speech as a musical phrase, and the phoneme would be a single note in that musical phrase. Just to give you an example, and yeah, don't blame me because like I'm terrible at singing, but let's go ahead with it. So, twinkle, twinkle, little star, how I wonder what ye are. So that would be your word, right? Your musical phrase, right? And the phoneme would be a single note, like twing, right? Twinkle, it's two phonemes. It's the same two phonemes together. So you stitch together phonemes in order to come up with the entire sound for a word. Okay, another example, if you're not musical. So I guess you have a visualization and an understanding of the classical visualization of an atom. So you have the electrons rotating the nucleus. In the nucleus, you have a couple of particles. You have the protons and the neutrons. They are stuck together, and together they form the nucleus of the atom. So these particles are the sort of the necessary individual elements that make up the entire nucleus. So in this case, the analogy would go, the word is the entire atom, and the phonemes would be the protons and the neutrons are stuck together. And perhaps like you can count also the electrons in. Okay, so I guess like you now have a better understanding of these phonemes, but this is like a deep concept, and it's a deep research area as well. And indeed, like the phonemes are studied by phonetics, and there are like people who study them. They're called phoneticians, and basically they put together their brains and they heard all the sounds produced in all the languages in the world, and they came up with what we call IPA, or the International Phonetic Alphabet. So this is a collection of all possible sounds uttered in human languages. And the cool thing is that you start with a base of symbols, and we have between 100 and 150 or 160, I believe. So these are like all the symbols that you can see here, right? So these are like these graphemes, like the symbols that you have. But then you can apply modifiers to these symbols to create new sounds. These modifiers have like a weird name, diacritics. And these are basically just like modifiers, like simple, like tiny symbols that you can add micro symbols to these symbols, base symbols, and it acts as a modifier. So they can, for example, add a distortion to the sound or more nasality to a sound, like the difference between n, and where you can hear way more of a nasal sound, for example. And so when you put together all of this combination, you come up with hundreds of distinct sounds. And so you can think of them as all the sounds that have been generated at some point in human languages. And these are a lot. This speaks volumes about the wonderful phonatory system we have, that is basically the system that allows us to generate speech. It's incredible engineering from evolution. Fantastic. Okay, but how many sounds do you think your typical language has? Do you think like it uses all the hundreds of distinct sounds? Well, that would be quite a lot and just difficult to have. And so what actually ends up happening is that languages just use a subset of the universe, say a set of the international phonetic alphabet. And for example, like Italian uses a certain number of phonemes. British English, for example, has, I believe, 44 phonemes. And there's an overlap between them, but there are also like phonemes that are only unique to Italian and unique to English. And a cool thing here is that so when we grow up and we learn our native language, basically what we do is we fix our phonemes. We are able to recognize these phonemes and to utter them properly. But then when we learn a second language, what we tend to do sometimes, or most of the times, is we overimpose our native language phonemes onto the target language that we are learning. And that's basically when you hear like there's different accents from people from all over the world, for example, speaking English, right? And so that's the case why, for example, Italians sound like this. They sound like this because they're projecting, they're using their phonemes, the phonemes like that are the closest to the English phonemes to utter sound. Like for example, say the phoneme like the, with me. An Italian would probably sound something like this, with me, because like there's that sound, the, really doesn't exist in Italian. And so they just try to use the phoneme in their language that's the closest to what they hear. And in that case, it would be just like a D. Right. So that's quite fascinating. It's incredible stuff. Okay, but now let's just focus on the English phonetic chart. As I mentioned to you earlier, there are, for British English, I believe, 44 different phonemes, many consonants, and a lot of vowels. And that's very typical of English. And that's also like why it's so difficult to pronounce correctly for non-native speakers, because the amount of vowels is incredible. Let's jump into this interactive English phonetic chart. And we have it down here. It's basically the same chart that we saw, but it's interactive. So we can listen to a native speaker uttering these phonemes and sample words with those phonemes in. Let me put my headphones on. Let's listen to these, to some of these vowels first. Like for example,
E.
That you can hear in
Sheep.
Sheep, or
O.
That you can hear in
On.
Good. And we have diphthongs as well. These diphthongs are sounds that are almost in between two vowels, like
Ear.
Right? That you can hear in here, right? Or
Ow.
That you can hear
Cow.
in cow. Good. Let's listen to some consonants. We have D for dog.
Dog.
And we also have this
The
one that's very difficult for us Italian native speakers.
This.
And this, of course, uses like that phoneme. Cool. Let's go back. Now that we have those symbols for these phonemes, what we can do is take the words as they are written, as they're spelled, and then translate them into this international phoneme alphabet. So the she bought 2 red apples, right? That's spelled in red. We can translate it in, with these symbols. And this is great because this transcription is connected directly to sound. So each of these symbols corresponds one-to-one, has a one-to-one mapping to a specific unit of sound. And this is great if you're doing text-to-speech, because now you have an alphabet that you can use that has a one-to-one mapping onto sounds. That's what you want to produce, right? And so we pass through this phonetic transcription and we can pass that information onto some model that takes that transcription, so it takes like those symbols that represent sound and then transform it into the relative sounds, because now we have a one-to-one mapping. Okay, but there are problems, and those problems go under the name of coarticulation. So phonemes don't appear in isolation. So we don't speak with individual phonemes, but we stitch them together to create words, and we then stitch words together to create entire sentences. But now we may have an idea on how to generate speech starting from phonemes, and it goes like this. So I know that all of these individual phonemes are individual sounds, and there's a way of mapping any type of sentence, word, directly onto these individual sounds, individual phonemes. So if I have the pre-recorded phonemes for pre-recorded sounds for all the phonemes out there, what I can do is I can concatenate them and generate speech. Because now I'm stitching together sounds that I have in a collection, and if I put them together, I can generate speech. Will that work? Well, more or less, yes. The concatenated phonemes, however, are going to sound robotic. But why? We've heard a lot of these systems like years and years ago, right? So they had like that very robotic sound before we had the amazing like deep learning models like 11 labs like we have today that are very realistic. But why that's the case? Why concatenating those phonemes doesn't really work? Well, if you think about it, the sound of speech changes based on context, okay? If I'm asking a question, I'm gonna like utter these phonemes and tie them together in a way like that's different than when I'm just talking in a neutral manner, right? So the sounds of those phonemes are gonna change, and also the interaction between those sounds are going to change based off of the phonemes that are connected together. And here we get, let's see, the next level of speech, which is prosody. What is prosody? Well, it's almost impossible to define perfectly, because it has all of these things like a rhythm, duration, stress, intonation, accent. See, all of these like aspects like that have to do with how we speak that most of the time are not easy to quantify. But prosody can encode both linguistic structure and emotion, and also meaning, as we'll see in an example very soon. But we can think of prosody as the musicality of speech. It's the way we speak, it's the phrasing, it's the rhythm. I can talk super fast, or I can talk very slowly, stressing different words for different effects. This is an interesting one to spot the difference in prosody. We're going. We're going. I'm saying the same thing. I'm using the same phonemes, but the prosody is different, right? And we can call this pitch contour. So the pitch, the frequency of how we utter a certain like sentence, for example. Here, this clause, we're going. In the first case, we're going, it's neutral. So the pitch contour is stable, but in the second, we have a question. Usually with a question, in English, we tend to raise the end of the sentence, the tail of the sentence. So we're going, right? And just through that pitch contour, prosody not only changes like the musicality of the sentence, but also encodes meaning. Because I know that when I hear we're going, it's not something that I confirm. I say, yeah, we are going in a neutral manner. I'm affirming that. No, it's a question. So prosody can carry also meaning. And that's why it's extremely important to have prosody injected into speech synthesis, because otherwise it's going to sound super flat and robotic because I don't have any prosody in it, okay? Prosody is not the only thing that makes speech what it is. There's also another aspect of it that is timbre and voice identity. So what's timbre? Well, timbre is the color or the quality of the voice, okay? And in music, it's quite straightforward. So you play the same note, the same pitch in a piano and in a flute. And even if the pitch is the same, so the frequency is the same, the duration of the note is the same, but you're gonna hear that note slightly different. And that difference is the color of the sound, is the timbre of the sound. The question is why every person sounds unique? Well, that has to do with the timbre of their voice. That's very unique to you. It's almost a fingerprint. And that is determined by the shape of your vocal tract, so your phonatory system. Just like our fingerprints are all different, our phonatory system and the shape of it is slightly different for each human being. And with different vocal tracts, we have also different resonances of the nasal and oral cavities that are necessary to generate sound. And also, there are also other aspects, like the habitual pitch we speak at. I can speak like this in a very deep and profound voice, or I can speak like this. It's me in both cases, but the pitch changes, the bass pitch changes. It's also like this like voice identity like changes like with age, and that's why like people tend to recognize like how old another speaker can be. It's not perfect, but you can get an idea. And also based off of health, if you have health problems in the phonatory system, of course, like you're gonna sound different because perhaps you have some impediments that otherwise you wouldn't have. So the timbre is really the fingerprint of a speaker. And in voice cloning specifically, what we try to do with our models is not only generate speech, but generate speech in a specific timbre. So we should find a way of capturing timbre. And again, that's not easy, because you see like all of these elements also kind of interact with each other. So you can't just look at them completely independently. Okay, so here we have phonemes, here we have prosody, here we have timbre. No, they co-interact, and that's the beauty and the complexity of creating voice cloning or speech synthesis systems that actually work. This video is offered by myself. If you're building an AI music, voice, or audio products and are facing high-stake technical challenges, I can help. I've been building AI audio companies and products for 15 years. I now offer consulting on architecture, R&D, product strategy and hiring, so you can avoid costly mistakes and months of wasted time. Visit valeriavelardeadvisor.com to book a strategy call, link in the description. Now back to the video. We now have talked about all of these different elements, but we really haven't talked about how we human beings do generate sound. How do we do it? Let's take a look at it. It's extremely interesting. So, a classic way of visualizing or modeling how we generate speech is going with this idea of a source filter model. So we have a source of sound or a vibration source that's created by the vocal folds, and we'll see how that happens more in detail in a second. But then we also have the vocal tracts, so the oral cavity, the nasal cavity, and all the other elements we have above our vocal folds that create a sort of resonant filter. So we have this source, this vibration source, and then we have a resonant filter on top of it that can cut a few frequencies here and there, boost other frequencies. And so depending on what happens there, we're going to generate like different phonemes in different timbres, okay? But if you're a musician, and I'm sure here on The Sound of AI, a lot of you guys like following these videos are musicians, probably you are familiar with the concept of subtractive synthesis. And this is an extremely famous synthesizer, probably my favorite ever. It's called a Moog. It's a subtractive synthesizer. So subtractive synthesis can be quite complex, but the easiest thing is that it, like the easiest way like of talking about it is with this like source filter model. So you have a source and it can be an oscillator like a sine wave or a triangle wave or whatever, right? A square wave. And then you apply some filters on top that change the sound. The theory is really good and everything, but it's always better to understand the thing by looking at some implementation. And what I found is a very nice subtractive synthesizer, very simple, but very nice. And let me show you how this source filter model works. As you'll see here in this synthesizer, we have a bunch of different components, but we're going to ignore all the components but for two. The oscillator that basically generates an initial wave. It could be a sine wave, a triangle wave, or a square wave. And then we have the filter. In this case, we have a couple of filters. So one is a low-pass filter that lets you pass the filters below a certain cutoff frequency, and a high-pass filter that just does the opposite. So we're going to be focusing only on this and listening to the results. Okay, so we have a triangle wave and we have a low-pass filter activated. That's the sound. Let's change the cutoff frequency. Let me change the resonance. You hear the difference, right? So what's happening basically is that we have the initial wave and we modulate that wave with the filter, and the filter obviously in this case has a couple of parameters: the cutoff frequency and the resonance. What the resonance does is basically giving a bump at the frequencies around the cutoff frequency, and so that's why you hear that difference. That's basically what happens when we produce speech. Let's go back to the phonatory system and the way we generate speech sound. And we want to revisit the source filter model and now go more in detail. So, of course, in order to generate speech, you need an energy source, okay? And this comes from the lungs, like that push the airflow. So this energy source goes up, up, and up through the trachea, and it gets to the vocal folds here, as you can see. And the vocal folds are the equivalent of the oscillator in our synthesizer. And so they basically start to move and they generate a sound that's called a glottal sound. Let's take a look at this glottal sound and what it is, okay? So it's a basic sound and it's generated through the fast opening and closing cycle of these vocal folds. This movement generates a quasi-periodic waveform, okay? Almost like a sine wave, but it's not really a sine wave, right? It's almost like quasi-periodic, right? The vibration frequency that you have like of this cyclic movement determines what we call F0. That is the fundamental frequency. Let me show you how it changes, like with my voice, for example. I'm going to do ah, okay? And I can do ah, or I can do ah. The sound, like the phoneme is the same. As you can see, the change in pitch is going to be determined by the amount of cycles like that I have in and this cyclic motion that I have in my vocal folds. Okay, in the latter case, when it was like in the higher end, of course, like the vocal folds were moving way faster. Okay, so now if we take like that sound and we move to the spectrum, the power spectrum, so that we can take a look at all the different frequency components that make up that sound, we'll see that that glottal sound has harmonics. So it has like other frequencies that are part of that fundamental frequency. Okay. But this is just like one type of glottal sounds. There are two types of glottal sounds. So the first one is the one that I showed you earlier, right? So like a, b, d. These phonemes generate a voiced sound where the vocal folds vibrate. It's basically like the case that we've just covered. But there's also another type of glottal sound that you can generate that's called a voiceless sound, and in this case the folds are completely open, so the air flows through the folds and it's a kind of noise-like sound, like, and phonemes that have like a voiceless sound are it's noise-like, so you really don't have those harmonics like that make up like a nice well-formed voiced sound. Okay, so let's go back to the source filter model. Lungs generate the energy, the vocal folds generate the oscillation and the glottal sound. Now we need the filter, and the vocal tracts, so the oral cavity, the nasal cavity, the pharynx, and so basically everything that's above the vocal folds is a resonant filter that's gonna filter out certain frequencies and it's gonna bump other frequencies. But while the vocal tract tends to be relatively stable, then we have like some articulators like that we can move, like the lips, the tongue, the jaw, that tend to change the like in a fine-grained manner the type of filtering that we do, and so they articulate like the sound, they articulate like the phonemes. Like hear this, for example. So I'm with an a and I'm gonna move to an e. You see, I just like move like my tongue, the way like I arrange like my tongue and the lips, and the resonant filters are going to change their shape, and that is going to change the sound. It's going to change the phoneme, actually. Okay, so here's your source filter model more in detail. Okay, so now what actually happens under the hood on a more mathematical standpoint or more acoustic standpoint is that the source, the glottal sound, has a power spectrum like this, where you have like the like frequencies, like energy, like in the fundamental frequency, and then the harmonics. And then what happens is we pass through the filter, okay? And the filter can look like this, okay? And so basically the filter has like some peaks, and these peaks are the resonances, right? It's where we have it's where we have like the boost in energy. And so here, obviously, like this is again like a spectrum, a power spectrum. So on the x-axis we have the frequency, on the y-axis we have like the energy, right? And as you can see, basically like at this frequency we have a peak that we call f1, and we have like a bump in the resonance there, and then we have another bump, f2, f3, f4. And what happens is that when we pass the source through the filter, of course the filter is going to modulate the source, and the speech output is going to be a function of the source modulated by the filter with all of these resonances. But what are like those f1s, f2s, f3s, and so on and so forth? Well, these are the amplified frequency regions that we call formants. These are the formants. If you've ever heard about like, yeah, this weird alien concept like formants, this is what it is. It's basically the amplified frequency regions, the bumps, the resonances in certain frequencies, and they are determined by the vocal tracts. And indeed, each person has a slightly different vocal tract, and so these formants, you can think of them as a person's fingerprint. But the formants are not constant. These resonances change when you change the vowel. So different vowels have different formants. So basically what happens is that when you change the position of the tongue of the lip, not the lips, of the lip, you're basically shifting formant frequencies, and so you change the vowel. So isn't that wonderful? I mean, like our phonatory system is basically a synthesizer, a subtractive synthesizer, right? So where we have like this oscillator here with the vocal folds, and then we just modulate the sounds, the timbre really, just by like our natural vocal tract plus the articulators with the lip movements or tongue jaw movements. It's incredible, and how rich the sound that comes out of this is. It's just incredible. So as I said, like the formants are what like make you sound like you, because it's really a fingerprint. Like me and you will have different formants, and as I said, like the formants will be different for different vowels. So let's take a look at this spectrogram, right? So here we have like time. So here like that there's a person who said e u a, right? And here we have the frequencies on the y-axis, and we can see the formants, right? And for E, you'll see that the formants are F1 is around, I think like it's 350 hertz, and F2 is around like 2500 hertz, right? But then when you move to U, as you'll see, like F1 and F2 changes, and same thing for F1 and F2 for A. Okay, so this is how we generate sound. Isn't it fascinating? But you may be thinking, okay, yeah, that's really cool for acousticians. It's really cool for phoneticians, people like who work like with human voice. But why should we care? Why should I care about the source filter model and formants? Well, it turns out that when you know how we do something, well, when you have that insight, what you can do is you can try to reuse that knowledge and that insight to have a machine simulating or reproducing like what we do. And indeed, a lot of the TTS, text-to-speech systems out there, especially like the one a little bit more outdated, tend to use this idea of a source filter with formants. So it's extremely important like that you have a deep understanding or a clear understanding of how we generate speech, because then that domain knowledge can inform your text-to-speech or speech synthesis systems. Okay, but we're not done yet, because we talked about timbre, we talked about the way we generate sound, we talked about phonemes, but we talked also about prosody, but there's more than that. There's another layer of complexity in human speech, and that is emotion and expressivity, right? Speech is deeply emotional and context-driven. Emotion changes prosody, pitch, energy, tempo. It changes everything, and it's very difficult, once again, to quantify. But let me give you an example, and I'm sure like, you'll have like no problem to recognize the emotion that I have attached to this simple sentence. Let's start. I'm fine. Okay. Second option. I'm fine. Third option. I'm fine! Sorry about that if it was loud. Okay, the first one was just neutral. The second one was kind of sad, depressed a little bit. And the third one was just angry. Okay? Yeah, and that's another level of complexity that you have in speech. The emotional layer that's going to affect prosody, it's going to affect pitch, energy, the rhythm, the phrasing. So I want you just like to think about the complexity of speech and how challenging it is to take such a complex phenomenon and have a machine reproduce it. Yeah, but the point I want you to bring home from this lecture is that speech is multi-layered. We've seen a lot of layers in speech. The layer of thought, and that is, it encodes meaning, and in AI, like that is like the text input. Then we have the level of language that we encode with words and grammar. And in AI, we moved from text to phoneme. Then we have the prosody that encodes rhythm, melody, phrasing. And we have in AI an acoustic model to try to reproduce that. And then we have the level of timbre, especially in voice cloning, when we try to have a machine sounding like me or you, for example. That timbre encodes who we are with our voices, our identity. And in AI, what we have to work with is a speaker embedding. We should try to embed the uniqueness of a speaker in some form. And then we have the waveform, right? And that encodes the air vibration that we output from our mouths. And the AI analogy of that is the vocoder output, if we're using a vocoder system. But I don't want you to get like into the nitty-gritty details at this point. It's just like beyond the scope. But what I want to point you towards is the complexity of speech and how multi-layered this phenomenon really is. And so now, in this course, what we're going to do really is we'll learn how AI replicates each of these layers with different techniques, with different approaches. What we're trying to do with speech synthesizers is try to get all of that complexity and replicate it in our systems. And so, I think after this lecture, probably you should be able to answer to that question by yourself. So why is text-to-speech, voice cloning, so hard to pull out? Well, speech combines a lot of levels. It has structure with the phonemes, fluidity with prosody, individuality, timbre, dynamics, context given by emotion. And humans learn all of that effortlessly since we are super young, but machines have to model each layer. They don't have the same luxury we have in being immersed in a speaking world and exercising our phonatory system every day for hours and hours. This was today's video. I hope you enjoyed it. If that's the case, I would really appreciate it if you could leave a like and subscribe to the Sound of AI channel so you're going to get all the subsequent videos in the series. That's all for today. I'll see you next time. Cheers for now.